So first, a little bit about me. I'm the cross-team technical lead for the Netflix UIs. I created the async data platform that all the Netflix UIs run on. I'm a member of the TC39, which is the JavaScript Standards Committee. And I've got about 13 years in the industry, formerly worked at Microsoft and GE before my time here at Netflix. And this is the story about how Netflix solved the big async problems by thinking differently about events. And I'm just going to rewind now. Let's just jump back 3 years. And I was just joining Netflix at the time. And the Netflix app, like most JavaScript apps, is asynchronous. And that means we've got a lot of asynchronous processes going on in the app at any given time. App is starting up, which means we might be waiting for the platform to load. The player, when you interact with the player, every time you click a button, we might make a data request, and then we might have sort of cancel that data request when you click another button. We do data access, of course. All the data access has got to be asynchronous. Animations, as you move from screen to screen, animations come in and out. Once again, asynchronous coordination going on there. And binding between the view and the model. As the model changes, we want to respond by updating the view. And so that's an asynchronous process as well. Now, any app that does a lot of asynchronous things is going to have asynchronous problems, right? And I'm sure lots of you are really familiar with these. Memory leaks from forgetting to say unhook your event handlers, race conditions, callback hell, and complex state machines. So having to create a lot of state to coordinate what's going on, like how many requests do I have right now? And are they in a complete state or are they in an error state? Having to introduce a lot of extra state to coordinate concurrency. And error handling. Error handling is really, really hard when you start doing async programming. It's not like in synchronous programming with try-catch. And so let's take a look at an example of why async is so hard. Right? So here's a kind of a typical function. It's not really a real function, but it's very similar to the type of code that you might see in the Netflix code base 2 or 3 years ago. So what's going on here is we're trying to play a movie. Now this big block of code is going to accept the movie ID. It's also going to accept the cancel button, and it's going to have a callback, which is going to fire when that movie has been authorized. So what we're really trying to do here is authorize a movie and then play it. And so as you can see, one of the issues that we run across is we have to store state because we're doing something concurrent. In this case, I might be trying to sort of initialize a player if it hasn't already been initialized, and I also might be trying to authorize a movie at the same time. And now that I'm doing these two things at the same time, I want to make sure that I wait till they're both done before I move forward. And so what do? I have to introduce these state variables into my app, basically tracking whether each of these processes are done. When they're both done, I can move forward. As you add more and more asynchrony to your app, you'll add more and more state to coordinate that concurrency. And over time, if you don't control it, that state can get out of control and it can just choke your app with complexity. The other reason why async is so hard is errors. You know, in the nice, wonderful world of synchronous programming, we've got try-catch, right? I can say execute A, B, and then C, and if anything happens in the middle of that that throws an error, it cancels and it propagates up, and I can catch it at any level up there. Not so much the case with async programming, right? As soon as we start doing async programming, try-catch is all but useless to us. Now we have to be responsible for forwarding up errors at every place that they might occur in different callbacks and keeping track of whether there's an error and forwarding it along. So that's another problem. Now another problem, beyond just error handling, is when you start dealing with events. And a lot of talks that talk about promises don't really address events. Events are something, especially that developers here at this conference have to deal with a lot. Probably even more than XHRs, you deal with events. And so forgetting to unhook an event handler is one of those problems that can just plague you for days and days. Trying to track down memory leaks for forgetting to unhook event handlers is really, really problematic. And so as you can see here, I've actually left in a bug. Because in this case, I actually never unhook from this event handler. And over time, these event handlers and closures will just keep accruing, and you'll eventually run out of memory. And so to understand how it got so bad, why is async so hard? Right? We're going to have to go back 20 years. So we're going to go back to 1994. 1994 was a good year. We had the Blue Album, right? Weezer's album. Speed came out. Good times, right? Good year. Who has this book? Who's read it? Keep your hands up. Okay, good, good. So pretty old book. This is when it came out 20 years ago. And to understand why async is hard, the answer actually lies in this book, which was released 20 years ago. And it all comes down to a simple little mistake. And I'm going to explain that to you right now. Who remembers seeing this diagram? You don't have to pay attention too closely. just for this diagram. This is the diagram in the back of the book that shows about all these design patterns and how they're related. This book about design patterns was really influential. It tried to take common patterns that developers were creating to solve problems, and it codified them so that we could just sort of refer to that and just implement the pattern without having to solve the same problem again and again. And then the designers wrote this nice graph for us, and they explained how all these patterns are related. But there's two patterns in here, iterator and observer, that they didn't say were related. There was no line connecting the two. And I submit to you that they are related. They're actually related very fundamentally. And missing this little detail is one of the reasons why async is so hard today. So how are an iterator and an observer pattern like each other? And what are they, for starters? Because these names sort of meant a lot back in the days of C programming, and maybe the average JavaScript programmer that might not be familiar with this pattern. So just quick show of hands, who knows what an iterator is? Who's heard of ES6 generators? So those are actually very similar. It's the same concept. In an iterator, what you do is a function can give you an object which you can pull data from progressively one item at a time. So here I've got this function getNumbers, which is going to give me an iterator. And then I'm going to call next on it, and it's going to give me this little tuple that's going to say, hey, here's the value of 1, and we're not done yet, which means I can keep calling next because there's more data. So I'll call next again, and I get value 2. And once again, it says, you're not done yet. You can keep going. So I'll call next again. This time I get 3. It says, you know what? Not done. The next time I call next, it finally says, you know what? You're done. So an iterator is a way of progressively pulling data from a data producer, one item at a time, until finally the producer tells you, we're done. So what's an observer pattern? Well, an observer pattern today is basically the precursor to PubSub, the precursor to the events that we use nowadays. Add event listener, event emitter. These are APIs you're probably familiar with if you've done any web development, right? So it's really kind of, in a sort of weird way, it's the same thing, isn't it? It's a data producer giving a data consumer items one item at a time. But it's sort of the other way around. It's sort of inverted. In this situation, I hand a callback to a data producer, and it keeps calling it over time, progressively sending me data. So if I subscribe and then move my mouse, I get this stream of data over time. Does that make sense? So how are the iterator and observer pattern related? They're both about a data producer sending information to a data consumer one item at a time. So what's the difference between the observer and the iterator pattern? The observer pattern, the producer iterates you. That's all it is. It's the other way. It's just the same process in reverse, right? So maybe you're not familiar with the iterator pattern. Maybe you're more familiar with the array, the JavaScript array, which we all know and love, right? So when I was working at Microsoft 5 years ago, a man named Eric Meyer asked me a question. He said, what's the difference between an array and an event? And the answer kind of blew my mind. And it got me so excited about this particular technology that I really couldn't wait to actually go and build a large-scale system on it. And so a few years later, I left and joined Netflix. The answer to this question is that there's really not much difference. There's not as big a difference as you think. Events and arrays are both collections, and we can think about them that way. So before I go on and explain how this works and why the observer pattern and the iterator pattern are actually deeply linked, we're going to pause for a brief JavaScript 6 tutorial. So the truth is this technology has nothing to do with JavaScript 6. I'm going to show you JavaScript 6 for 2 reasons, and 2 reasons only. One of them is that I'm on the TC39, and I want people to get excited about JavaScript 6. And the second is that JavaScript 6 allows you to write the same program with much less code, and consequently, I can fit it on small slides. So if you'll bear with me for this brief JavaScript 6 tutorial, it'll be over before you know it. Functions today. In JavaScript 5, this is how you create a function, right? In JavaScript 6, you can get rid of all that boilerplate, and you can condense this down to this. I will pause for applause. Yeah. And that is the end of the JavaScript 6 tutorial. You're all experts now. So what I'm going to show you guys is something I think is pretty amazing. The majority of all of Netflix's async code, and there's a lot of it, is written with just a few flexible functions. Moreover, these functions on close inspection are going to seem to have nothing whatsoever to do with async programming. And they're functions you already know in all likelihood. And so bear with me. So this one barely even counts. We all know for each, right, over array, right? It allows us to traverse a collection and then output the data, right? So if I run this on my fake PowerPoint slide console, you will see that I output those values, right? You'll have to trust me that works in real life. Who knows map? Who knows the map function on array? Yeah, so, okay, good. You guys are pretty familiar with it then. So if I take 1, 2, 3, and remember, arrow means function. This is the new JavaScript 6 function syntax, right? If I take 1, 2, 3 in an array, and I apply a function to every single one of the items in that array, I create a new array, and I want to emphasize, I create a new array. I don't change the previous array. I create a new array of all of those items translated after running them through the function. So if I add 1 to every item in this collection, I create a new collection of 2, 3, 4, right? Pretty straightforward. Filter. I'm assuming you're pretty familiar with filter if you're familiar with map. So pretty much the same thing, except this time we're going to apply a test function to every single item in the collection and get a new collection of only those items that passed the test. So if we apply this, what are we going to get? 2, 3, right? Okay, pretty straightforward. Now, concat_all is not a function that exists in JavaScript. I wish it did. But it's really simple. It's easy, obviously. You could always add it to the prototype. But it's very simple. It takes a multi-dimensional collection, and it reduces it by 1 dimension. So it takes a 2-dimensional collection and flattens it to a 1-dimensional collection. Or a 3-dimensional collection, flattens it to a 2-dimensional collection, and so on and so forth. Which means that if we take this and flatten it, we get 1, 2, 3, 4. Now, I want you to notice something. When flattening a multi-dimensional collection, if one of those collections is empty, it just disappears. That's going to be important later. So just take a note of that. So quick review, map, filter, concat_all. Everybody got this? Pretty straightforward, right? So who's a Netflix user here? I know you're out there. Yeah, lots of Netflix users. Great. So this is our new UI for televisions. We call it the Darwin UI because it's actually evolved from all of our A/B testing over the last year, which is something that we do intensely. I think it's great. And if you've used Netflix, you're pretty familiar with the model. It's a relatively straightforward model, right? We have a lot of genre lists, and within each genre list, we have a lot of titles. And so it's basically like, you can think of it as kind of a 2-dimensional array, right? So we have genre lists, and inside of that, titles. So let's see if I can use map, filter, and concat_all to get a list of your favorite Netflix titles. How hard can it be, right? So here I'm creating, using that nice sugary new syntax, get top-rated films, which when passed to user, will go through that user's video lists, will map through each of those video lists, and return those video lists, but first it'll filter each video list, grabbing only those titles with a rating of 5. Now that's going to leave us with a 2-dimensional collection, because if you map over a bunch of video lists and return another collection, well, that's necessarily a 2-dimensional collection, right? So we're going to take that 2-dimensional collection, we want to flatten it down into a nice stream of your favorite titles. And so we apply concat_all to that 2-dimensional array, and we get something that we can for each over and output. Is that pretty straightforward? Yeah? So what if I told you that I could create a mouse drag event with nearly the same code? Possible. Yeah, there we go. I love audience participation. It never gets old. So I want you guys to look really closely. Look close, you're going to miss it, OK? So here's how we get the top-rated movies collection. And here is my mouse drags collection. So obviously, same structure of code. Take a close look at this code. I want you guys to imagine that events are collections, first-class collections, just like an array or an iterator. They're objects that you can map and filter. And if that's the case, we can write code very much like this. So what is a mouse drag event? Well, a mouse drag event is basically mapping over all of the mouse downs from now to eternity. And for every single one of those mouse downs, we want to return a collection of all the mouse moves from now until eternity. Now, before we return those mouse moves, we are going to transform that collection into a new collection by applying this new operator, take until. In the previous example, we reduced the number of items in a collection by using filter. In this example, we're going to use this new operator, which I'll explain later, take until, which reduces the items in the collection. It basically is going to listen to all of the items in mouse moves and just push them on through. But as soon as it gets a mouse up event, it's going to complete that collection, like ending an array. And now, if I return this collection for every single one of these mouse downs, well, I've got a 2-dimensional collection, just like in the last example. And so how do I flatten the 2-dimensional collection down into a 1-dimensional collection? Concat_all. And so with concat_all, I can now for each over the result, just like I would an array, and write the various positions, or actually literally change the position of the image. And this code works. You can drag around an image with this code. So how do I do it? How is this possible? Well, it's possible because of a new data type called observable. An observable is like an iterator or an array, and it's basically a collection over time. It's a collection that arrives over time. And so when you for each over an observable, unlike an array, it doesn't just jump to the next line after blocking and consuming all the elements. If you for each over an observable, it will immediately go to the next line, and then as those elements arrive, we'll run that callback. And so it's a collection that arrives over time. This observable type is introduced in a library called Reactive Extensions. It came out of Microsoft. It's open source. And it's been ported to a whole variety of platforms. Netflix actually uses this same asynchronous model on the client and server. And so we actually have an end-to-end asynchronous solution that uses observables. So observables are great for UIs because they can model three things that we use in UIs all the time. They model events, data requests, and animations. And they can model it in such a way that we can combine all these things, glue them together seamlessly in a way that you can't with promises. Now, if I want to convert a regular old event to an observable, it's as simple as this. So I can use this from event helper function that pass in a DOM element and then give it the name of the event, and I get out an observable. And now this is something that I can map and filter and do all the operations that I showed you earlier. So what's the difference between an event and an observable really? I mean, they're both sort of like pushing data at you, right? It's pushing data at you over time. But there's one crucial difference, and I'll talk about that in a moment. An observable can complete, and an event cannot. Remember back in that iterator example that I showed you? Iterators, the producer can tell the consumer, I'm done. You notice that with DOM events, there's no well-defined way of being able to say, you know what, I'm done. There's no way for the producer to tell the consumer, I'm done. And so just by adding that one semantic to the observer pattern, the ability, a well-defined way of a producer to say to the consumer, you know what, there's no more data coming to you, we can actually approach programming with iterators or arrays in exactly the same way as programming with events, just by adding that one missing piece. Furthermore, subscriptions. Remember I mentioned how hard it is to make sure that all of your events are unsubscribed when you're done with them? Well, imagine that instead of unsubscribing from an event, you could declaratively describe the conditions under which that collection ended. That's take until. That's what take until does. Instead of me building a state machine and saying, when this event fires, I'm going to go and unhook my subscription, I use take until to declaratively say, you know what, I'm going to create a new collection out of this event. And this new collection is going to end when this other event fires. Now, the wonderful thing about having a collection that can tell you it's done is with an observable, it will unhook your subscribers for you. As soon as an observable finishes, there's no reason for it to hold on to your subscription anymore, because it knows it's never going to give you any more data. This small change, this small addition of being able to say I'm done, fundamentally changes the way that we approach event-based programming. This whole problem of subscriptions and remembering to unhook them and this mechanistic approach totally goes away. You just describe the conditions under which the collection ends, and then it cleans up for you. So let's take a look at this event subscription. This is how we do it, you know, in my world, in the bad old days. I would hook up to an event, and then at some point later, I would remove an event listener. Now, an observable allows me to do the same thing. So it's just slightly different interface. You know, here we for each, we pass in console log, and we for each with it. So it's just like adding an event handler. But when we for each over an observable, it gives us back the subscription object. So this is very similar to like clear interval or clear timeout. For those of you familiar with that event, we get back this little handle on that particular subscription. And if we want to unhook from the event, we just call subscription dispose. So these two, just based on looking at these two examples, there's not really that much difference, right? They both support the same things. You can hook up to an event. You can unhook from an event. You can hook up to an observable and listen for things. Excuse me. You can hook up to an observable and listen for data. And you can unhook from an observable. But observable has a couple of tricks up its sleeve. So for each has a couple of more handlers that you can pass here. See the second and the third? The second is for receiving an error that happens anywhere in that asynchronous expression that we wrote earlier. So if an error happens anywhere in an observable expression, it bubbles all the way up, just like with try-catch, to where you're for eaching, and you can catch it, essentially, right there by providing a handler. So it's very similar to the way promises work. And the final callback is that important semantic that we talked about earlier. Observable will call you when that stream is completed. So you can do things when the stream is finished. And so just those two additional callbacks, that's the main difference between an event and an observable API. An observable is a real object, and it will propagate any errors that happen throughout the expression all the way up so that you can catch them in one place. And finally, it'll call you and tell you it's done. So that's the basic type. Now, to understand how an observable works, it's one thing to be able to think about it. It's another to be able to visualize it. So what I'm going to do with your guys, if you'll allow me, is I'll create this fake literal here for an observable. So let's make up a syntax. Now, I warn you, this syntax is not in JavaScript 6. But it's just there for you guys to be able to understand how an observable works. So here we see a collection arriving over time. Let's imagine each of these dots was like 1/10 of a second or something, right? So now you'll see that I can take an observable and I can for each over it just like an array. The only difference is that elements arrive over time, right? So it's exactly the same way as for each worked over an array. If I map over an observable, what happens? Same data comes out, it just arrives over time. Filter. Once again, same thing you would expect from an array, just data arriving over time. And finally, let's take a look at concat_all. So concat_all is kind of interesting because it orders operations. You ever notice that concat_all is going to work top to bottom, left to right? It's going to start with the first collection and end with the last collection. So you're always going to get items in the right order, left to right, right? We're always going to get 1, 2, 3, 4. Now, when you're doing asynchronous programming, you can't always rely on order quite the same way, right? If I make 3 concurrent requests or I subscribe up to 3 events, just because I subscribe to them in a certain order doesn't mean I'm going to get data back in the same order. And that's part of what really leads to race conditions. So wouldn't it be great if we could somehow use some sort of operator to make sure that data always came back in the order in which the collections arrived? So that's what we can do with observable. With observable, we can model a 2-dimensional collection. Most problems in UIs are actually best modeled, most asynchronous problems, as this structure right here. Think about it. I click a button, and I send off an asynchronous request. And then I click the button again, and another asynchronous request goes out. And I click the button again. All of these asynchronous requests can overlap. It's really 2-dimensional because of this addition of time. And so you can see here these observables. We have an observable, inside of which we have inner observables arriving over time. And so at first we get this observable here, and it immediately fires 1 at us. And then maybe like half a second later, or overlapping, we get another observable, and it immediately fires 2. Now, while we're waiting for that observable to fire 3, so currently we get 1 fires down immediately. While we're waiting for this next observable to fire 3, another observable comes along, but it just happens to be empty. And so it just disappears from the data set. And then, right after that finishes, another observable comes along, gives us 4. We still haven't gotten 3 from that initial observable there. So we're waiting on that. So what concat_all does is it makes sure that elements arrive in the right order, despite when they actually arrive. And we can use that to actually resolve a lot of race conditions that you come across. And so what we're really doing here is we're taking a 2-dimensional collection and flattening it. And I submit to you, that's really what most asynchronous programming is fundamentally about. It's about taking multi-dimensional operations that happen with that dimension of time and figuring out how we can flatten it down such that it's a flat stream again and things happen in the right order. So let's take a look at us using something like that. So before we do that, though, I'm going to explain how take until works. So take until is really simple. We just listen for a source collection. And as data arrives, we push it through. And at the same time, we're listening for a stop collection. And so we get 1, and then 2, and then the stop collection fires, and so we end the overall collection. So that's what allows me to listen for mouse moves until a mouse up happens, and then basically unsubscribe from both of those events and say, I'm done. So the key thing here is with take until, we don't unsubscribe from events anymore. We just describe when the collection completes, and we never leak memory. So back to this mouse drags example. Now you guys actually have better tools to understand how this thing works. Once again, let's go over it. I map over each one of these mouse downs. For each one of those, I return a mouse up, or a mouse moves collection. Now that creates that 2-dimensional structure that we saw earlier, because for every mouse down, we've got this new collection arriving over time of these mouse moves. And that's what that 2-dimensional collection looks like. So for every single one of these mouse moves we return, we apply take until to make sure that that collection stops when we mouse up. And then finally, we flatten it with concat_all using the strategy you guys saw earlier. Does that make sense? Yeah. Cool. Doesn't blow any minds? Anybody's mind blown? Great. So let's tackle something a little harder. Now, earlier I said that observable could model events, asynchronous requests, and animations. Right? So that initial example just showed us combining events together, which is great, but you know what? Most things that we do in a UI start with an event, are followed by an asynchronous request, and then end with an animation. So let's at least show an example of taking an event and then an asynchronous request and how we can combine them together. So who's done an autocomplete box before? Yeah, lots of UI devs have tackled the autocomplete box. One of those problems, it seems like it should be kind of easy, but isn't really. There's lots of challenges around building an autocomplete box. I'll tell you, one thing that comes right to mind is if I type A in Netflix search, and then we go and make a request for it, and then before that request comes back, I type B, and now we make a request for AB. Is there any guarantee that the request for A will come back before the request for AB? No, you'll end up showing the results for A on top of the results for AB, right? So that's one of the problems that is really kind of tough to tackle. And you need to build some complex code to solve that problem. Another problem with Netflix search or your typical autocomplete box is if I type A, B, C, D, E, F, G, do I want to send 7 requests? No, I probably want to send 1, right? So we want to throttle, and that adds another element of asynchronicity. So how do I build a drop-down list using Observable and Rx? Well, let's see, what collections do we have? What collection do we start with? Well, we start with this key presses collection. Right? I'm going to take that event, I'm going to model as an observable. And then it's just a stream of keys that happen over time. Now, I'm going to apply this helpful throttle operator available on Observable, and that basically turns A, B, C, D into A, D, and so on and so forth. Basically slows down the rate at which items come out of there. And then I map each one of those keys, and I call this getJSON function. Now, this getJSON function is basically going to return me an observable of 1. It's like a promise. It's an observable that's eventually going to give me an array of all the search results. But now I have my race condition, because I've got this two-dimensional collection, because for every key press, I'm creating this new observable that are arriving over time, these new observables that are eventually going to give me data. But they could give me data in the wrong order. So how do I avoid that? Well, I apply take until. As soon as you make another key press, so as I press A, we send off a request for that search results data. And then as soon as you press another key press, as soon as you press B, we will take that outgoing request for the search results for A and complete it. And by completing it, basically make that collection empty. And we know what happens to empty collections when we flatten using concat_all. They essentially disappear. When I first wrote autocomplete, I didn't think about this problem in terms of streams at all. I thought about it in terms of states. Well, OK, so you've clicked the button. I've got an outgoing request. I move into the outgoing request state. And now, oh no, you've clicked another button, so I've got to unhook my handler and move back to the original state and then move forward again. I don't think about problems that way anymore. That's a really hard way of thinking about problems. It's much easier to visualize things as collections with a few very small operators that can combine those collections together at a high level. And so, as you can see here, I also apply an operator that I can use on an observable that I cannot use on a promise, which is retry. It's very, very common that you will get intermittent network failures when you're doing async requests, right? They happen all the time. So promises don't allow you to retry. Now, you can call the original method that gave you the promise again, but an observable will actually allow you to retry because it's lazy. Every single time you for each over an observable, it's going to trigger another async request. And so I can use this retry operator to make sure that if there's a sporadic intermittent network failure, we'll try again 3 times before we actually forward on that error up to the for each statement at the bottom where we can catch it. Does that make sense? And so by doing take until key presses, we make sure that we've completely resolved the race condition. And none of those outgoing observables ever overlap. As soon as one is outgoing and we start another one, we just end the one where it was before. And concat_all flattens this into a nice stream of all the search result sets that ever happened from now until eternity. And then I just for each over that, and I update the state of my UI. Notice what I've done is I've separated my code into 2 distinct parts. One that I'm basically creating an event from simple events. I'm taking simple events and creating a much larger, more complex event that has exactly the data that I want. That first part, everything above the fold on this slide, is just taking data and computing new collections from it. I haven't changed a thing. I'm just taking collections, translating them into new collections. Finally, when I've got a collection that gives me just exactly the data I want, I for each over it, take that data, and I use it. I update UI elements. I write it out to a log. I push it out over a stream. So over time, you see that your code actually bifurcates into 2 parts, creating expressions, creating new data, and then changing state and using it. And over time, more and more code is going to make its way into the former category, and less is going to make its way into the latter category. And that's a very good thing, because there's a whole class of bugs that just can't happen above the fold there. When I'm making a state machine, the problem with state is that it gets set wrong. Right? It's easy to mistake and somehow set a variable before you set some other variable or set a variable to the wrong state and essentially end up in a broken state. In this situation right here, there is state, obviously, but it's being handled under the hood for me. The state's not my problem anymore. I'm visualizing this thing as just a series of collection interactions and translations. Does that make sense? Yep?
Sorry, just a quick question about the code. So the one thing that's subtle here is the for each block below the fold, as you say, is obviously executed with each incoming key press, not when the whole collection of key presses is over. I mean, it's happening every time a new object comes in, right?
Well, so specifically that callback will only happen when you actually get the search results back from the server. So we'll get the result sets. Now, in practice, some code is being executed for every key press, but who knows, maybe that network request fails, or we get several more key presses happen, which trigger new network requests, which cancel the previous ones using take until. And so by the time something actually comes out in that for each, it's the data that we want. We've created an event that we want, a more specific event from simple events. Now, we do this with functions all the time, right? We take little functions and combine them together to make big functions. But then when we move to events, we don't do it anymore. And there's not a good reason for that. Compositionality is good. The reason why we don't do it is because it's hard. We didn't really know how to do it cleanly before. It was a really hard problem to be able to build up complex events that register event handlers all over the place, and yet somehow also be able to tear them down cleanly. That's what's been solved here. You should approach events the exact same way you approach functions. You should combine them together to make more complex ones that are exactly what you want. Does that make sense? Any questions about the slide before I go on? OK, I'll jump forward to the Netflix player. So the Netflix player, this is another example, just another example to sort of reinforce it. The Netflix player has a lot of asynchronous stuff going on, right? As soon as you decide to play something, you might cancel. You might leave the page, right? You might press stop or pause. All those cases, we might want to respond by stopping whatever asynchronous process we've kicked off, like authorizing your ticket, for example. So let's take a look. Let's come full circle and take a look at the callback hell that we had earlier here and see what we can replace it with an observable. So really, it's not that I have a function that I want to win past a movie, try and authorize it, and do all this mechanistic stuff. Really what I want is I just want a stream of movie authorizations. That's the event that I want. What I actually have is I have an initialization observable that will get fired from the player whenever it actually initializes. I also have a call that I can make to authorize a specific movie, and that will give me back an observable that will fire whenever that authorization comes through. Those are the basic events and collections that I have. I'm going to combine them together to create the collection I want, which is the authorizations collection. So everything starts with player initialization. I have to wait for player initialization before I go forward. So I map over all the player initializations. Now, the fact is there happens to be one item in this collection, but that doesn't matter, right? If I map over just one item, that works just fine. And for every single one of the player initializations, I return all the play attempts, and this is like the collection of all the attempts to click play on movies, right? And for each one of those, I map over the movie IDs, and then I issue an asynchronous call to authorize that movie ID, and I get a ticket back. Once again, same structure as before, some user input followed by some asynchronous request, right? But now I've got a race condition again, right? What if you cancel? Or you go to another and you try and play another movie, and I end up playing the old one after it gets authorized. I want to cancel it. I want to make sure that we're always looking at the latest thing that the user wanted to do. This is really common in UIs. And so it's the same structure as before. I listen for play attempts, and every single play attempt, I'm going to listen for the data that comes back from that authorization until a cancel happens. Either you hit back or stop or anything else, right? I'm also going to retry just in case that request failed for just sporadic network failure. And finally, I'm going to take that two-dimensional collection and I'm going to concat all. But now that whole collection was returned within the outer player init observable. And so basically I'm 3 dimensions deep now. So it's just 2 concat alls to flatten everything down into one flat collection. And now I've created the event that I really want, the event I wish I had, which is authorizations. I just for each over it, just like subscribing to an event. And for every authorization, I attempt to play with that license that I got back from the server. Now, if an error happens, in other words, an error that actually gets retried 3 times and it's actually down. So we know the server's down. Netflix has got great uptime, but you know it happens every now and then, right? So if that thing fails, after 3 attempts to retry, see that on-air handler at the very bottom there? I handle it in one place. And it just looks exactly like I would with a catch, right? I can handle any error that happens within that entire operation right down there, and it'll get bubbled up. Does that make sense? So in Netflix, we use observable everywhere. We don't really use promises, certainly not in any of the device UIs. And the reason for that is that a promise is an observable that fires once. It's a subset, right? I can easily create an observable that just fires once, and then it can do anything a promise can do. Furthermore, it can do more than a promise, as I called out earlier, because I can retry. A promise is essentially what we call a hot data source. It's going, and by the time you get it, there's no way to retry it, at least not on that promise itself. You have to call the original API, but that's not compositional. And the other thing about it is that there's no way to cancel a promise, as I called out earlier. Right? At least not the TC39 promise that's going to be released with JavaScript 6, which, if you were to build a Venn diagram of the number of asynchronous requests that I make that I never want to retry and never want to cancel, none of them would fall in that Venn diagram. So for us, observable is a much better way. I'm not saying promises aren't useful for certain things, but if you're making outgoing network requests, I think observables are much more useful. So we use observable for app startup. We use it for the player. We use it for data access, for animations, and view model binding. Any questions? More on observable? Yep.
You might go back one slide.
Yeah.
So coming out of it, would you ever have multiple authorizations? I understand it's an observable, but would you ever play multiple or authorize multiple?
Well, we don't currently allow it. You never know, maybe new feature. But in the moment, you can only play one thing at a time, right? So essentially, when you try and leave and cancel and play another movie, I want to cancel that authorization, right? But if it was a promise, if I was using a promise, there would literally be a call that's going out to the server. Now, some people might say, you know what? If you send something off with an XHR, there's no canceling it, right? How do you cancel? Well, some XHR APIs do actually support cancellation, right? You can cancel an outgoing request. But a lot of UIs, and I'm sure there's people in this room who have this, they essentially have a queue. So you don't just fire requests off whenever anybody wants something. You put it into a queue, and then eventually you send it off. Because WebSockets are precious. And often some calls have higher priority than others, which means you can legitimately, often in many cases, prevent a request from going out because it's just sitting there in a queue waiting to be sent out. That's a very valuable thing for the response time of your application. There's no reason to send out requests that are like old, that people don't want anymore. And it's very common with UIs for people to request something new. They are fickle. They get bored. They decide they don't want to watch that movie. Yep?
So in this example, play attempts and cancels,
where are they coming from? Good, because there's a little magic here, right? Well, I'll show you exactly. Remember the observable.from event that I showed you earlier? This helper function? I'll show you exactly how I would build those. I would just call observable from event, and I would pass in the DOM element for the play button, and I would pass in the DOM element for the stop button. That's a simple explanation. Right? Anytime you want, you can take a DOM element that's an event and convert it into an observable. And then you can use it compositionally in exactly the example that I showed you later on. It's that simple. Yep?
Can you compare and contrast observables and node-style streams if you're familiar with?
Yes. Great question. Who's familiar with node-style streams? Okay, because I know this event is mostly focused on developers, I think, on the front end, a lot of HTML dev comp. But for those of you who don't know, node-style streams are Node's answer to asynchronous I/O, meaning if I read from a file on Node, that's going to be asynchronous. It's going to call me back every single time it reads something. Now, it's not going to block when I call read, because that would be bad. There's no reason to block on I/O. So when I call read, it's going to read some data and then call me back when it's done. Now, I might take that data and I might decide to write it to some output. Now, even that write operation isn't going to block. It's going to say, OK, you're done, and then call me back when it's actually finished. So that can be kind of complicated because we're reading asynchronously and we're writing asynchronously. And what happens if the read is faster than the write? What happens if I'm reading from local disk, but I'm writing over a 3G network, for example, right? It's very possible that that read could happen much, much faster than the write. And it's kind of complicated because I've got to wait for every write to finish before I sort of put the data in. So how do I do that? I mean, either I could wait until every write operation was finished before I started another read operation, but that would be really slow because I would sort of only be able to write as fast as I could read. So what often people will do is they'll add a buffer. So as they read, even though they read much faster than they write, they'll add that data to a buffer that grows and grows. And then when it grows to a certain point, they'll stop reading and then flush that buffer. And that leads to much, much faster throughput. And so the main difference between node streams and observable, there's really only one primary difference. Node streams is basically an attempt to encapsulate this pattern of reading and writing, but stopping if we get what's called back pressure. So in other words, if the writer says, you know what, slow down, you're going too fast, I can't write that fast. We have this notion of back pressure where the writer can say, you know what, slow down, just wait a second, and then maybe the reader can collect up data, keep collecting up data in a buffer, right? So what differentiates a stream and an observable is much more powerful in terms of composition than a stream. The operators like concat all, for example, what does that really mean to a stream? It's complex. There's no real similar operators that are expressive and as powerful in node streams. However, node streams can do something observables can't. Node streams can say, cool it, you're writing too fast. Observables are only push, and iterators are only pull. Node streams are both. Node streams allow you to push, or rather, node streams allow you to sort of push, but then also pull and send back information that says, you know what, slow down, cool it. Now, in practice, node streams aren't that important on UIs. In fact, most of the UIs, most of the APIs you use for writing data that you get from a stream on the UI in the browser are synchronous, or at least they're synchronous as far as you know, right? It's what do you do with that data you get from asynchronous streams and events? Usually you pump it right into the DOM. And the DOM, essentially under the hood's kind of got a buffer of its own to some degree. It buffers up changes and makes all those changes at once, and that buffer itself might even be the event loop. But the point here is that node streams, that inability to respond to back pressure, just doesn't really matter that much on the client. It matters on the server, and there's work underway to figure out how to address that issue, how to address that scenario. It's similar to events. I don't think you can do very much to guarantee order. If you have 2 observers or 3 observables all subscribed to the same observable, I don't think there's really any way that you can sort of control the order in which those observers fire, much the same way that you can't with DOM events. We're trying to basically build a better event to some degree with an observable, an event that's compositional. And so we don't really have a provision for that, per se. You could accomplish that, but not quite the same way. If you wanted to order it and make sure that 3 different people got that response in order, well, it's possible to do that with the operators, actually. There's several operators that will allow you to do that. But 3 observers to the same observable, you're not really necessarily going to be guaranteed any particular order.
Do you have an external library that is used for this, or is Netflix just using internal?
So good question. I don't know if I mentioned it earlier, but it's the Reactive Extensions Library. It's a open source library. I highly recommend you guys look up RxJS. It's available as a node module. Go to the RxJS website. And it's called Reactive Extensions. It's totally open source, free to use, and it's very mature. It's been around for quite some time. So yes, it's an external library.
Does every observer bind to the observable in its own way, or is it just one binding?
The question was asked, does every observer bind to an observable in the same way? Now, by that, do you mean if I add an observer to an observable, is that like going to share the same data as another observer going to an observable? I see what you're saying. Right, if I subscribe 2 observers to the same observable, and then I unsubscribe the first one, does it affect the other one? No. Each subscription is essentially independent. So in practice, what that would mean is, let's say I had an observable that makes a network request. Now, the thing about observables is they're lazy. This is what's the difference between an observable and a promise. A promise is eager. By the time you get a promise, work's already being done. An observable, by the time you get it, nothing has happened. In fact, everything above the fold in that example that I showed you earlier, we haven't started doing a thing, not a single thing, until finally we call for each. So everything above the fold here has not started a single async request. It hasn't done a thing. It hasn't even subscribed an event to key presses. It's not until we for each that all those event handlers sort of ripple through the expression and get hooked up. And so observables are lazy. Now what that means is, if you subscribe an observer to an observable that's lazy, it's going to kick off a network request. And then if you come along and subscribe another observer to the same observable, it's actually going to kick off a second network request. Now that might not be what you want. Sometimes you want to just have multiple concurrent listeners for the same network request. And sure enough, there's an operator to do that. So it's called publish, actually. You can take any observable and basically publish it so that no matter how many concurrent observers you have, they're all going to share the same side effect under the hood. That side effect may be hooking up an event handler, might actually be sending off an XHR. But the point is, observables can be cold or hot. You can set up an observable so that it actually will start doing some work and sharing it amongst all of the folks listening, or you can set it up to be lazy and do something new and fresh every single time. So it's inherently more flexible than a promise. Sorry, what was that? Bacon.js. Yes, I'm glad somebody brought up Bacon.js. Bacon.js was actually based on RX. So RX was around before Bacon.js. Now, Bacon.js is based on the idea that observables should only be hot. I hope I got that right, because I'm not 100% familiar. But the idea was, I think the author thought that it was confusing to have both cold and hot observables. And so it would be just better and all around easier to teach if we only had hot observables. I respectfully, actually, I would probably agree with that. It's definitely simpler, but it's also really powerful to be able to mix cold and hot observables. And so that's why the API is actually nearly exactly the same between Bacon.js and RxJS. So I would say that over time, as you find your applications needs become more numerous, you'll find cold observables are very helpful. And at that point, you can graduate up to RxJS. Sorry if I didn't make that clear earlier. Cold and hot data sources. Hot data source is a mouse move. Something's happening whether you're listening or not. And if you start listening 10 seconds later, you'll get a different data than if you start listening 10 seconds earlier. Right? A cold observable is like an array. An array, no matter whenever you for each over it, you're always going to get the same data out. It's essentially always just going to be finished for that matter. Does that make sense? Here's what's great about Rx. If you have events, you can make events better with Rx. And almost every framework has events, right? And this is completely orthogonal to things like Angular and Ember. Angular and Ember are about organizing your application and propagating model changes to views, but they have events. Every single one of these frameworks responds to events. Rx is going to let you take those simple events that they expose either through the DOM or directly, like mouse move, mouse up, and actually combine them into more complex events. And then you can just go for each over it and do exactly what you would have done if you'd subscribed to the simple event. And just essentially update your view or update your model. Totally orthogonal to what Ember and Angular and React, Facebook's React, do. And it works very, very well, the two of them together. All you have to do is convert their events into observables. And there are helper functions to help you integrate into those various libraries to make it easier to take their particular event flavor and turn them into observables.
Where can we go to learn more about this?
So resources. So the truth is, we've actually had to teach this technology to a heck of a lot of developers. We've probably got, I don't know how many UI developers we have now, a heck of a lot more than when I joined. And in order to be able to scale this up, from our perspective, this technology was so great and solved our problem so thoroughly, the technology wasn't the hard part. It was actually teaching developers. Most developers, like you and me, grew up with loops. We grew up thinking about things in terms of loops. And the reality is, next 10 years of programming, loops are going to be less and less important and useful. Why would I say that? I say we are near the end of the loop. Why would I say that? Why are loops potentially not as useful as they were 10 years ago, 20 years ago? Parallelism, yes. Parallelism, right? If let's say I've got a huge array of numbers, and I for loop, I read a loop over those numbers, and I accumulate up all those numbers into a sum. I want to sum all those numbers, right? Well, if I make a counting for loop, I've kind of specified a lot of information about how that sum actually happens. I've kind of said, you know what, start at the beginning of the array, and then go all the way to the end of the array and sum everything up left to right. Well, maybe 5, 6 years ago, that algorithm got twice as fast every 2 years. It just kept getting faster. I would kick my feet up, and I would just come into work like 2 years later, my program would run faster. Awesome, right? Not so much lately, right? Last 3 years, that algorithm doesn't run much faster. And I've got a dual core, and I even have a quad core desktop at one point. Wasn't getting any faster. Why is that? Why is it not getting any faster anymore? Or not much faster, at the same rate, certainly. No. Individual processors are not getting faster. Processors are not getting faster. They're multiplying. There's more of them. We're getting dual cores. We're getting quad cores. Heck, you get quad cores on some phones now, right? Problem is that algorithm, that loop algorithm, is not getting any faster because it's only running on one of those things, on one of those cores. How do we describe our algorithm in terms of what we want to happen, instead of how, in excruciating detail, we want it to happen? That's what map and filter and reduce and scan and many of these other functions essentially allow us to do. Describe at a high level what it is we want to have happen instead of how to do it. The great thing about telling the computer what you want to do it instead of how to do it is that that computer can take a look at runtime conditions, how many cores are busy, how many threads are available, and make dynamic decisions about how to run that. Now, We've got JavaScript programmers in here, right? We're not so worried about threads, right? We've only got one thread. What do we have to think about multi-threading for, right? It's not our problem. Guess what? It's your problem. It's your problem because I and a few other folks are making it your problem on the TC39. We are introducing parallelism, shared memory parallelism into JavaScript. We're looking at doing it right now in JavaScript 7. So why would we do this to you, right? Well, we want HTML5 apps to actually compete with native apps, right? If we want them to continue to compete with native apps in terms of their responsiveness, we have to give you the ability to leverage all this extra computing power. Now, we're not giving you the ability to just new up a thread. We don't trust you. We don't even trust, I don't trust myself with threads, right? What we are doing is we're giving you a safe way of handling parallelism, and that's map. Map is a safe way of doing parallelism, right? You're not saying start over here and end over there. You're saying to all of the items in this collection, apply this transformation function, right? We can take that collection, you can split it up into 4 parts, do it on 4 cores, put it back together again. You're none the wiser, right? This is coming in JavaScript 7. And so the key to the next 10 years of programming, not just solving for concurrency, but also solving for parallelism, is what we call vector programming. This notion of thinking about programs as basically collection transformations. And the more and more of your code that you can express as collection transformations, you know what? It's going to keep getting faster. Not forever, but at least for the next, hopefully, 5, 6, 10 years, you're going to be able to kick your feet up, come into work, and find that your program got faster, every 2 years. And that's a great thing, right? So if I don't know how to make a stronger case that you need to learn vector programming, right? Learn vector programming, or become a manager or something. Developers need to know that. Any other questions?
When are you getting rid of Silverlight?
When are we getting rid of Silverlight? I think it's. I think you're. I can tell you that we're definitely working on it. We're definitely working on it. Actually, Matt, my VP back there, might be able to comment. Matt, do you want to say anything about that? Just want to make sure I don't speak out of turn. Anybody else?
When I look at some of the syntax with RX, it looks a lot like Link.
Yeah.
With Link, you have things like you have some enumerable structure.
Right.
You can say it adds a parallel, you can partition your data, and kind of effectively declare the hints to how you want to process a big map.
Right.
Would that apply here, and why would it apply not?
So, little secret. RX came out of Microsoft, and you can compose observables with Link. So the question was, RX looks like Link. Link is a technology that come out of C#, which is a programming language that Microsoft uses. And the truth is, you can use Link, it's a little SQL-like language inside of the programming language. You can absolutely use Link to put together observable. RX is available for .NET, and that's exactly where RX came from, using Link to compose events together. So yes, it is Link. Sorry.
So in the notion of vectors, sometimes you have like a position and another position and one, and you want to be able to actually make the vector, right?
Well, when I talk about vectors, I should be clear, because I'm not talking about like SIMD programming or anything. Well, actually, technically, it could be SIMD programming. I'm talking more about just collections, collection transformations, right? Oh, like an item and then the item next to it. So like pairs, moving across pairs, right? It's actually reasonably easy to do that. Well, first of all, you can do it with operators. So you can, like, pairwise is an operator you can write over an observable and essentially just store that one item and then give you pairs along the way. So there's no reason to use a loop to do that efficiently. I could actually write that over a stream efficiently as well by just caching the last value and then just giving you a stream of pairs. In fact, you can use an operator called zip and skip together, and maybe I'll show you an example. We'll talk about that afterwards, maybe a little bit. Any other questions? So one thing I do want to call your attention to is this link right at the bottom here. This is the tool that we use to train our developers, go all the way back from loops, gradually to teach you how to program this way. And it's a series of online JavaScript exercises you can fill out right in your browser. We teach you how to solve problems with loops, and then we teach you how to solve problems compositionally, with functional programming, with vector programming. And so try out this link at the bottom there. Go ahead and visit that. And I definitely want your feedback. We've trained 50, 60 developers, both server and client, to use RX using these exercises. And so we want your feedback on them. Any other questions? Okay, thanks everybody.